Greetings, this video is for Calc 2 and I wanted to clear up some questions about summation shifting indices. So first let's start with a simple example. Let's say I have a function f of x that's equal x raised to the n. Very simple function. And remember that this is a function of x, so x is the variable and n is some parameter of the situation in the function. If I take the derivative of f, then that's going to be equal to n times x raised to the n minus 1. Let's move that fast forward then to a summation situation. So f of x equals the summation from n equals 0 to infinity to x to the n. Now, if I wrote out this first few terms, well, when n is equal to 0, I'd have x to the 0. So I'm actually going to write that out. And then plus x to the first, plus x to the second, plus x to the third, plus, and then that would continue on. Now let's look at what happens when I take the derivative. So I'm going to take the first derivative of the same idea. That's the summation of n equals 0 to infinity, x to the n, and I'm going to make this notation with the prime notation. And then that's equal to, now if I take the derivative of each of these terms, so this first term up above was x to the 0, and x to the 0 is equal to 1 as long as x was not itself equal to 0. And so x to the 0, and then take its derivative as 0. So the first term in this situation would be 0. And the next term would be the derivative of x to the first is just x, and I take its derivative and I get 1. And then the next one would be 2x to the first, and 3x squared, and so on and so forth. Okay, so that's what the derivative would look like. So now what I want to do is algebraically modify this to show what the derivative looks like. So I have the derivative of f is equal to the summation from n equals 0 to infinity of n times x raised to the n minus 1. And then that's equal to, so when n is equal to 0, I'm going to have 0 times x raised to the negative 1. Plus, when n is equal to 1, I'm going to have 1 times x raised to the 1 minus 1. And then plus, I'm going to have 2 raised to the x raised to the 2 minus 1, or 2 times x raised to the 2 minus 1. And the next one will be 3 times x raised to the 3 minus 1. And that'll go on forever. And when I simplify this, I see that, well, this is 0 times x to the negative 1, so this is 0. And then the next one would be 1 times x to the 0, which is 1. And the next one would be 2 times x to the first. And the next one would be 3 times x to the 3 minus 1, and 3 minus 1 is 2, so this is 3 times x squared. And that'll go on forever. So we can see right away that indeed using this notation produces the same derivative as when I took the original and took the derivative of each term separately, right? So the idea then is, well, look what happened here. I have the summation of n equals 0 to infinity of n times x to the n minus 1. And the first term of that situation, when I plug in n equals 0, is 0. And so I'm actually adding a 0, right? And so when we just add zeros to things, we don't change its value any. But mathematicians tend to not like that, right? It doesn't look very nice when I just have this string with a 0 there, right? I have a 0 and I have a 0. And it's not wrong, it just looks funny to us. So often what we do is then change the indice to not start at n equals 0, but start at n equals 1 to infinity of n times x to the n minus 1. And when I write out all the terms of the second one, well, n equals 1, I get 1 times x to the 1 minus 1, so that's 1 times x to the 0, which is 1. And the next term would be 2, and so I'd have 2 times x to the n minus 1. So that would be 2x, and the next one would be 3x squared, and so forth, right? So the important thing to see here is that I change the indice of those two summations, but they are exactly the same. So I changed the index to start at 0, and I changed it to start at 1, but I didn't have to change the actual rule of the summation, because those two rules are equivalent when n starts at 0 or when n starts at 1. And the reason for that is when n starts at 0, my first term is 0. When n starts at 1, my first term is still 0. I just don't write the 0, right? My first term that I write on the paper is 1, but the terms are exactly the same. So sometimes I change the indice because I don't want to put the 0 out front. It's not sort of fashionable in mathematics to write plus 0, but the value didn't change. So these two, n equals 0 to infinity of n times x to the n minus 1, is exactly the same as n equals 1 summation to infinity of n times x to the 1. Even though the indice changed, their value is exactly the same. So that's the first scenario. Sometimes we change the indice because we're not really trying to add zeros to things. It's not mathematically fashionable to do that. Now let's look at another scenario. This is a completely different situation. Again, I'm going to start with this very simple summation n equals 0 to infinity of x times n, or x raised to the n. So in this situation, if I applied the 0, first, what do I get when I do all my terms? Well, I get x to the 0, so this is x to the raised to the 0th, plus x to the first, plus x to the squared, plus x to the third, and so on and so forth, all right? So this is equal to 1 plus x squared plus x cubed plus dot, 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 and I go on forever, right? So, very simple. But now I have to be careful, because if I decided to change the indice from n equals 0 to infinity, that summation of x to the n, and I wrote a quality, and I said that that was the same starting with 1 x to the n, the trouble here is this is incorrect. This equality is not true anymore. So I changed the indice, right? I started from 0 and I changed it to 1, but now they're not mathematically equivalent. Why? Well, let me write out the indices here. X to the n starting with 1 is x, and then x squared and x cubed and so forth. All right, so when I change the indice, the one over here on the left, the first term has a 1, and then all of these things. The one over here on the right, the first term, there's no 1, right? So as it turns out, this one, if I take the summation of n equals 0 to infinity of x to the n, that's equal to 1 plus the summation of n equals 1 to infinity x raised to the n. This is a true statement. Why? Well, because, as I said before, this with the n equals 1 to infinity, x raised to the n is equal to x plus x squared plus x cubed. And then if I add 1 to that, I get the same thing that when I did the summation that I have written on to the left. So sometimes when I shift, like I did up here, sometimes when I shift indices, it doesn't matter, right? Because I am starting by adding 0 to the terms. So whether I add 0 to the first term or I don't write the 0, it's fine. Mathematically, it's sort of unfashionable to write a plus 0. But sometimes it absolutely does matter, because when I shift the indice, I leave out a term. So how do we fix that? Well, let's actually write where I fix it. Okay, so let's say then that I wanted to switch this n equals 0 to infinity of x to the n to a summation of n equals 1 to infinity. I wanted to transform that, and I need a new rule to make this work. So then the question is, how do I find that new rule? So what I do is I think, well, I'm starting with n equals 0. That's what I'm starting with. And I want to transform that somehow to n equals 1. That's what we're trying to get. And so what I do is think, well, if I subtract n minus 1, I get 0. All right, so I subtracted 1 from both sides of this equation. So then I get n minus 1 is equal to 0. So then I think about it is I then need to put everywhere I see a n, I need to write an n minus 1. So let's try the summation of n equals 0 to infinity of x to the n is equal to n minus 1 equals 0, summation to infinity, and then I have x raised to the n minus 1. So that's what I did. Wherever I saw n, I substituted in n minus 1. And so when I simplify this, this is a summation. And so I'm adding 1 to both sides of that equation down there. So this is a summation as n equals 1 to infinity of x raised to the n minus 1. And now let's see what happens when I write out the first few terms. Well, when n is equal to 1, I have x to the 1 minus 1, which is x to the 0th, plus when n is equal to 2, I have x to the 2 minus 1, which is x to the first, and then x to the squared, and so forth. And that would go on forever, right? And so this is then equal to 1 plus x squared plus dot, dot, dot. And so, as it turns out then, I can write this with equality. The summation as n equals 0 to infinity of x to the n is exactly the same as the summation as n equals 1 to infinity of x to the n minus 1. And so in this case, I shifted the indice from n equals 0 to n equals 1. And when I shift the indice from n is equal to 0 to n is equal to 1, I have to change the rule to preserve equality. And that is the case sometimes when we're dealing with summations. But remember, that is much, much, much different than before in the first example, when I shifted the indice only so that I wasn't adding a 0. Okay, I hope this video helps clear up some questions. If you have any more questions about this subject, please let me know.